Welcome back to Module 5, Blockchain Security and Digital Identity. In this lecture, we will explore security risk analysis of blockchain-based applications. First, we will learn about security risk management and security risk management principles. We will explore security risk analysis of healthcare case, where we will present blockchain as a countermeasure solution. We will also perform security risk analysis of blockchain-based applications, where we will explore cyber attack and double spending attack in more detail. According to CHAISE learning outcomes, after this lecture, you will be able to explain blockchain as a countermeasure solution, as well as you will be able to explain what type of security threats can appear in blockchain-based applications. This lecture has three main objectives. First, to explore security risk management and how blockchain can act as a countermeasure solution. Blockchain-based applications are not prone to attacks, and there are various security threats that can appear in blockchain-based applications. So we will explore what type of security threats can appear in blockchain-based applications and how to mitigate them. So let's get started. Security risk management. Security risk management is concerned with lowering the risk of intentional unauthorized harm to valuable assets to that level that is acceptable to system stakeholders by preventing and reacting to malicious harms, misuse, security threats, and security risks. Managing security risks include identifying, analyzing, and treating security threats to maintain the system assets' confidentiality, integrity, and availability. As we previously stated, the security risk management is a process that is concerned with lowering the risk of intentional unauthorized harm to valuable assets. In accordance with this, we follow the security risk management domain model that enables a systematic approach to analyze the security of information systems and provide the key concepts and relationships supporting the definition of security and security risk management. Security risk management domain model addresses the security risk management process at three different conceptual levels. For example, in the perspective of assets related concepts, risk related concepts, and risk treatment related concepts. The assets can be classified as system or business assets and play a vital role in accomplishing an organization's objectives. The business assets are items of value and describe the information, processes, capabilities, skills essential to businesses. And the system assets supports the business assets. Security criteria, for instance like confidentiality, integrity, and availability, are business assets constraints or properties because security criteria distinguish the security needs of business assets. In risk-related concepts, the risk is a combination of risk event and impact. The risk event constitutes the threat and one or more vulnerabilities that negatively impact one or more assets by harming them. In contrast, vulnerability is a characteristic of a system that depicts its weaknesses or the flaw. The threat agent uses an attack method and triggers the threat that targets one or more system assets by exploiting their vulnerabilities. Risk treatment related concepts present decisions to treat the security threats by defining the security requirements. Security requirements are implemented as the security controls. For example, countermeasures implement the requirements that mitigate the security risk. The security risk management domain model explains the relationship among assets, risks, and risk treatment related concepts that establish a process combining different activities to perform the security risk management. For example, using this security risk management domain model, first we categorize the context by exploring what assets to secure and determine the security objectives requirements in the context of confidentiality, integrity, and availability. Second, we identify the security threats that exploit various vulnerabilities in traditional applications to harm the assets and negates the security criteria of business assets. and how blockchain mitigates those security threats that categorizes under countermeasure concepts. Third, we identify the security threats that may appear within blockchain-based applications and define the security risk management decision to treat the threats by incorporating the countermeasures. The process of security risk management is not static. Therefore, the process of the security risk management enables it to perform several iterations to reach an acceptable level of each risk. As we previously said, security risk management is concerned with lowering the risk of intentional unauthorized harm to valuable assets to that level, not to completely or 100% mitigate the risk. It is just to reduce to that level that is acceptable to system stakeholders. So, we will focus on the security requirements that help us to mitigate the security threats to that level that is acceptable to system stakeholders. To move forward with our security risk analysis, we will use a healthcare case which is related to back pain patients treatment. In this healthcare case, back pain patients application illustrates the interaction of various stakeholders to give medical treatment to back pain patients, where the medical advisor prepares a letter which we call CNAM letter. This CNAM letter includes questions to expert doctor and necessary medical reports. The patient delivers this letter and medical reports to the expert doctor. The expert doctor registers the patient data and defines illness type. For example, like it is a work accident or long duration illness, just like it came by sitting for long or it is something inherited illness. The expert doctor performs the patient physician examination. For example, it measures the weight, height, build, limb and gait and writes a conclusion based on the gathered data. The expert doctor writes a medical report and sends it to the medical advisor. In this case, the case scenario presented in the previous slide has three main stakeholders. For example, the medical advisor who prepares the letter, the expert doctor who tests and decides on treatment, what type of treatment this patient is needed, and the patient who needs treatment for his back pain. So, the scenario starts when the patient contacts the medical advisor for consultation. After the appointment, the medical advisor prepares the CNAM letter, including questions to the expert doctor, and attaches the necessary medical reports if needed. The patient is then in charge of delivering the letter and the medical reports to the expert doctor. The expert doctor registers the patient data and collects additional information during the interview to define illness type. For instance, like previously stated, like it is work accident or long duration illness. For example, during the interview, the expert doctor collects whether the patient suffers from low back pain, the type of illness, whether the patient is diabetic, and also asks for personal information, for instance, like marital status, number of children, and the last job type or the current job type. Therefore, the expert doctor identifies the illness and studies the necessary documents related to either the work accident or the long-term illness. Next, the expert doctor performs the patient's physical examination and records the results. During the physical examination, the expert doctor can check and verify the consistency of the claim. Then the expert doctor writes a conclusion based on the gathered data. For example, like on the patient details, he can conduct an interview with him and physical examination outcomes. So, all these type of data he will gather and will write a conclusion based on that. The expert doctor writes a medical report and sends it to the medical advisor. This report includes the conclusion about the patient medical status and guides the medical advisor regarding the decision. For example, whether the medical leave is needed or not, what is the duration of the medical leave, and when the patient could return to work. We will consider this back pain patient's healthcare application case to illustrate the security threats and how they can be mitigated using blockchain technology. So first, this case which we are presenting is built on centralized applications using the traditional technology infrastructure. And now we are going to present what type of security risk can appear within these centralized traditional technology infrastructure and how blockchain can act as a countermeasure solution to mitigate those security threats. So let's explore. So we will use the security risk management domain model as a foundation of our study to perform this security risk analysis of traditional healthcare case. We perform the security risk analysis of back pain patient healthcare application, identify the security threats of traditional healthcare applications that can be mitigated using blockchain. For example, data tampering and data theft are the most concerning security threats of traditional healthcare applications. Following the other security threats, for example, like records mishandling, man in the middle, where the attacker can sniff or get information during the communication. There is a single point failures because there is a centralized server or centralized system which is handling all the operations and services of the applications. So there is a single point failure by running denial of service attack or distributed denial of service attack or flooding the request to the systems. Then there is a security attacks related to repudiation and social engineering. So in the upcoming slides, we will explain these security threats in detail and their countermeasures based on the blockchain. So we gained the knowledge during the security risk analysis of healthcare applications and mapped on back pain patient healthcare application. The analysis we performed helps to identify the security threats of back pain patients healthcare application that are highlighted as security threats points. The attacker can manipulate these security threats point by exploiting different vulnerabilities associated with each threat point. So let's explore these threat points one by one. So threat point number 1, which is related to the data tampering. So due to the weak access control to share the CNAME letter, the unauthorized user, for example, the attacker or the malicious user, can get access to this letter and tamper with it. Also, there exists a possibility that a patient can intentionally or unintentionally can tamper this letter. In both cases, the system does not have a proper mechanism to verify and validate the legitimacy, authenticity of the CNAME letter. The next threat point is again related to data tampering and data theft. So in the data tampering threat can happen on medical reports because the system has a weak centralized access control mechanism. Thus, an authorized user can access the patient medical reports and tamper with them. In the current system, the medical reports are stored in human readable format, for example, like in plain PDFs, documents, and X-rays, and no proper cryptographic controls or encryption mechanisms are implemented. The attacker can access them to pursue various activities or various targeted campaigns related to insurance frauds, wrong drug prescriptions, and ransomware attacks. The data theft undermines the confidentiality of medical reports and patient privacy, eventually jeopardizing the integrity and trust in a back pain patient's healthcare application. Furthermore, the patients have weak control over their medical reports in back pain patients' healthcare application. For example, medical institutions control and manage patients' medical data where non-relevant individuals can access and manipulate it, either intentionally or unintentionally. Also, this traditional back pain patient's healthcare application does not guarantee the authenticity of electronic medical records. Threat point number 3 is related to man in the middle attack. The attacker can exploit the weak controls of secure communication to get medical records, medical reports, and a CNAM letter. Moreover, due to the lack of data anonymization, the medical records are associated directly with the patient's identity. With the man in the middle, the attacker can sniff the data to pursue various activities. For example, publish the data online or deny patients access to it, or ransomware attack. A successful man in the middle attack can affect the data exchange, medical records, medical reports, CNAM letter, and communication assets. Threat point number 4, the patient medical data is critical, and the healthcare system should trace all the actions performed over time. For instance, either intentionally or unintentionally, all the changes should be recorded. The back pain patient's healthcare application case, which is built on traditional technology infrastructure, does not use immutable logs to maintain track of all the actions taken on a patient medical data over time. There exist some techniques to keep logs in traditional environment, but those logs are maintained by single authority or designated authority, and also those logs cannot verify the authenticity of the logs. For instance, if you will change something in the logs, you cannot trace who made the changes in the logs. So as a result, the existing systems lacks a means for proving the modifications on a decision of patient's medical status. In threat point number 5, there is a chances of weak centralized access control that refers to a situation in which the system fails to prevent unauthorized access to the database. So in traditional technology infrastructure on which the back pain patient's healthcare application case is built, there are chances of the unauthorized users can get access to the database and to their records, to the patient records. The attacker breaches security and performs unauthorized actions that negate the integrity of medical records and healthcare databases. Currently, the back pain patient's healthcare application has no security or cryptographic controls to protect the database from data theft attacks. Overall, the security threat negates the confidentiality of medical records, healthcare databases, and patient's privacy. Also, the back pain patient's healthcare application, which is built on traditional technology infrastructure, has a centralized database server and network services. The attacker can locate the flaw in the design and or implementation of the system and cause database overhead or disable the medical services, and essentially shutting down the whole system. In the threat point 6, back pain patient's healthcare application is also vulnerable to social engineering, where patients and hospital personnel are the weakest links. The attacker can get easily target them using social engineering tactics to get the CNAM letter. So, the successful social engineering attacks can violate or can impact on the CNAM letter and the patient privacy. So, here on this slide, we have listed all the vulnerabilities which are related to different security threats on different security threat points, which we discussed in previous slides. For instance, the vulnerability 1 is related to weak centralized access control mechanism. There are chances in the system either doesn't have a access control mechanism, or it has a weak centralized access control mechanism that is managed or controlled by a single or designated authority, and it cannot prove the authenticity of those access controls. Second vulnerability is related to no proper mechanism to verify and validate the authenticity of the CNAM letter. For instance, there are some changes or modifications done either intentionally or unintentionally. The system does not contain a functionality to verify and validate the authenticity of CNAM letter. Vulnerability 3 is related to no cryptographic controls, or either having a weak cryptographic controls which are easier to to be attacked from the malicious users. Vulnerability 4 is related to patients have weak control over their medical records, because the medical records are managed and controlled by the organizations, for instance, hospitals, research institutes, or other pharmaceutical companies. So, patients do not have any control on their medical records. And also patients do not know what different organizations are doing with their records. Vulnerability 5 is related to no guarantee of electronic medical records authenticity. Again, this comes towards the authenticity of the records which are stored on the database. So, the traditional technology infrastructure does not implement verification and validation of the data by design. So, there are high chances there is no guarantee of electronic medical records authenticity if they are tampered or modified. Vulnerability 6 is related to weak controls to secure communication. Vulnerability 7 is related to lack of anonymization of patient data, because the patient data in the databases is stored according to the identifiable information of patients. So, anybody can either from the hospitals or other research institutions, or either the attacker can get his hands to the data of patients, and then they can recognize which patient, which data is belong to which patient. Vulnerability 8 is related to no immutable logs, because the logs which are used are stored in centralized technology infrastructure. There are high chances people can modify them, then they can remove the traces. So, there are no mechanism to verify these logs are authentic or not. Vulnerability 9 is related to no mechanism to identify intentional or unintentional data changes. For example, there is chances of repudiation in this case. Vulnerability 10 is related to improper security controls for a centralized database. Vulnerability 5 is related to relying on a centralized server. So, it means there are high chances of single point failures or system overheads. So, the attacker can flood the system with the requests, and then they can halt the services of medical services. Vulnerability 12 is related to weak controls to manage a large number of requests. So, there is no mechanism to handle those large number of requests. Vulnerability 3 is related to possible to manipulate patient or employee to get data access to the CNAM letter. And vulnerability 14 is related to the attacker can persuade the patient or medical advisor to get the content of CNAM letter, which is related to social engineering techniques. So, we will present now we will present blockchain as a countermeasure solution to mitigate the previously discussed security threats and their vulnerabilities. So, blockchain provides different characteristics, different mechanisms by design that can help us to mitigate the discussed security threats. So, let us explore one by one. For example, the countermeasure model presents blockchain as a countermeasure solution, and it is illustrating the blockchain-based back pain patients healthcare application that implements various security controls by design and mitigates security threats of traditional back pain patients healthcare application. For instance, I highlighted various sections on this blockchain based back pain patients healthcare application scenario, where different security controls are implemented by design which providing by blockchain that are mitigating the various security threats. For instance, the blockchain based back pain patients healthcare application enables role based access control mechanism, which is a decentralized distributed access control to restrict who has access to the CNAM letter. Moreover, it provides a consensus mechanism to verify and validate the letter transaction without requiring a third party. A unique hash ID of original CNAM letter stored in the blockchain to verify its authenticity and an immutable ledger to keep track of each performed action. Similarly, the medical reports can be protected against data tampering using role-based access control and using and blockchain based controls to verify and validate the authenticity of medical reports. Role-based access control and using cryptography, for example, to store only encrypted medical reports on chain, overcome the threats of data theft. Also, the permission settings and role-based access control enables patient to control their medical reports, and tamper-resistant environment of blockchain and the tamper-resistant environment of blockchain guarantees the authenticity of medical reports. Blockchain-based back pain patient healthcare application works on a peer-to-peer based distributed network to exchange data, for example, like medical reports, medical records, and it makes for the attacker harder to intercept the communication, data analysis, or sniffing. Blockchain enables pseudo-anonymity because in back pain patients healthcare application, the patients and their medical records are linked with the public addresses, not the information which is recognizable for the patient. Like you cannot recognize which data belongs to which patients because it is just associated with a cryptographic address. Blockchain-based back pain patients healthcare application has an immutable ledger that keeps immutable logs to track who and when the particular operation, either intentionally or unintentionally, is performed. Thus, overcoming the repudiation threat, medical records and healthcare databases can be protected against data tampering by using role-based access control and blockchain-based controls to verify and validate the authenticity of medical records and the healthcare databases. Furthermore, decentralized and distributed access control, for example, like we are discussing here, the role-based access control, which is built, which is implemented using the smart contracts and deployed on decentralized environment, and there is in blockchain we are also using a strong cryptographic techniques to encrypt and to store the medical reports in the encrypted format. So these techniques can overcome the threat of data theft. Back pain patients healthcare application is running on decentralized environment, and the blockchain infrastructure itself is operating over peer-to-peer network and does not rely on a single or central point server and service. Thus, we can say that it is resilient to a single point failure. Blockchain-based back pain patients healthcare application employs role-based access control mechanism to guarantee that only relevant people are designated authorities to some particular to perform some particular operations have access to specific information, and unauthorized users cannot access medical records or medical data in the application. So here are some countermeasures which blockchain is providing by design. For instance, countermeasure 1 is mitigating vulnerability 1, 4, 13 and 14, and the countermeasure is related to decentralized access control. This access control is built or we can say like implemented using smart contracts and deployed on a blockchain which is providing decentralized and distributed environment. So for instance, if someone is going to make some changes in these access controls, all the participant nodes on the blockchain network have to verify this change, and if this change is illegal or invalid, then they will discard. So we can say that the decentralized access controls have more legitimacy or more power in context of verifying and validating the authenticity of the access controls which are implemented. Countermeasure 2 is related to blockchain-based controls to verify and validate the authenticity of medical records. Countermeasure 3 is related to consensus mechanism and mitigating vulnerability 1 and vulnerability 2. We discussed various consensus mechanisms previously, like proof of work, proof of stake, delegated proof of stake, practical Byzantine fault tolerance. So these consensus mechanisms provide us a control over the operations which are performed in the blockchain. So if, for instance, like if there are some invalid transactions occurred, or the attacker can introduce some invalid transactions or modifications to the ledger or to the patient records, for instance, like in our healthcare case, then during these consensus mechanisms, those records which are illegal or invalid can be discarded. Countermeasure 4 is related to immutable ledger. Countermeasure 5 is related to peer-to-peer network and mitigating vulnerability 6 and 11. Countermeasure 6 is related to encrypted medical records on-chain and off-chain. So it means like all the medical records which are stored on blockchain network, they are also encrypted, as well as all the medical reports and medical records related to patient which are stored off-chain, not like on a blockchain but off-chain, they are also encrypted. For instance, like on blockchain, we cannot store HEFI files, for instance, like PDF or X-rays or MRI reports. So those reports we store off-chain, but we can compute a hash of those reports, and we can store on-chain. But anyway, we have to protect those reports as well. So we store off-chain in off-chain storages using some again like encryption techniques, not like just storing in a raw format, like how it was done in centralized technology infrastructure based backend patient healthcare application. And countermeasure 7 is related to encrypted communication and mitigating vulnerability 3, 6 and 10. Countermeasure 8 is related to medical data are linked with anonymous public address and mitigating the vulnerability 7. This means like the medical records which are stored on-chain or off-chain, they are not directly linked with the patient identifiable information, but they are but we are using now some cryptographic addresses to link those medical records, so making them like a pseudo-anonymous. Vulnerability countermeasure 9 is related to permission settings. For instance, like in permission blockchains, we can have some permission settings to we can say like to give controls to specific individuals who can perform specific transactions or operations on the decentralized applications. Also in permissionless blockchains, we can also implement some permission settings using smart contracts. Countermeasure 10 is related to tamper resistant environment of blockchain, which is mitigating vulnerability 5 and 10. For instance, like if some change, invalid change or invalid modification is happened, then during the consensus and validation process, this change can be detected and discarded. So now moving forward, I have here listed the one famous quote of Bruce Schneier regarding technology and security problems. He said, like, if you think technology can solve your security problems, then you don't understand the problem and you don't understand the technology. So what it means? It means blockchain is not solution for all the security threats. And blockchain is a technology and it has various security threats as well. Either those security threats are inherited from different technology infrastructure which blockchain is using, or the new security threats are appeared in blockchain based applications or blockchain technology. For instance, here I have listed few security threats. For instance, like cyber attack, double spending attack, eclipse attack, smart contract attacks, linking attack, where we call like de-anonymization attacks. Although blockchain based applications are considered less vulnerable, they did not become the silver bullet for securing against different security threats, because different security threats are observed within blockchain based applications as well. And all these security threats which are listed here, they can be observed within the decentralized applications which are built on top of using the blockchain. For example, like in our case, we are discussing the healthcare decentralized application, the blockchain based back pain patient healthcare application. It can suffer from the cyber attack, double spending attack, eclipse attack, smart contract attack, and linking or de-anonymization attack. So, for instance, like such security threats appear after introducing blockchain in healthcare application. And here we will discuss cyber attack and double spending attack more in detail. So, cyber attack is not entirely like a blockchain based or blockchain specific attack, but it is related to a peer-to-peer network. So, cyber attack is a peer-to-peer network attack where attacker creates numerous fake identities and connects with victim nodes to isolate them from other honest nodes on the network. Blockchain system run over the peer-to-peer network as we previously discussed, and therefore it is susceptible to cyber attacks. The attacker targets the peer-to-peer network and negates the integrity of transaction business assets. So, our business asset is like here transaction, and the security criteria we defined is integrity. So, if the cyber attack happens, then the integrity of transaction is going to be violated, and our system asset here is peer-to-peer network. So, for example, in this case, the attacker can control several nodes on blockchain based healthcare applications by creating fake identities to gain a large influence on the blockchain network. So, for instance, like once the cyber nodes which are created by the attacker can gain the recognition on the blockchain network, the attacker can force victim nodes to process blocks under his control, or he can outvote or block the honest nodes to participate in the networks. The attacker can also use cyber nodes to interrupt the flow of information, distort the block generation process, and refuses to receive or transmit information. Also, if blockchain system has insufficient computing power, the attacker with higher computing power and cyber nodes can disrupt the healthcare operations. Moreover, the poor implementation of node authentication, for example, like not implementing any network joining fee, not validating IP addresses before someone is going to join the blockchain network, or the source of node connection. So, all these activities, all these actions, if we are not performing, then there are chances the attacker can come to the blockchain network, and using cyber nodes, they can negate the integrity of transaction verification process. To perform a cyber attack, the attacker has to identify the victim node. For example, your node, which is highlighted in green, and then replaces peers of that node with the attacker nodes. The attacker nodes are the cyber nodes which the attacker created by using the fake identities or fake nodes. Next, the attacker isolates the node and disconnects the transaction initiated by the node. Now, the attacker node involves a victim node to participate in their governed blocks. Here, the victim node has left only a single connection with honest nodes, and if the cyber nodes would successfully or would succeed in disconnecting this one connection, then the victim node will join the cyber nodes, and then they will participate in their operations. And by using the power of these honest nodes, they can gain more influence on the blockchain network, and then they can perform different illegal activities. To overcome cyber attacks in blockchain based healthcare applications, there is a possibility, there is a mechanism to use the node validation process before listing new nodes on the network. There are other countermeasures to mitigate the cyber attack in blockchain based healthcare applications. For example, incorporate network joining fees. For instance, like whoever is going to join the network asks network joining fee. So in that case, the cyber attack, every time he's going to register a node on the blockchain network, he has to pay a fee. Or you can put a condition on stake requirements in the proof of stake consensus to make identity creation more expensive for the attacker. Monitor node behavior to spot any unusual activities of nodes and disconnect them from the network. For instance, like if there is some unusual activity detected, immediately disconnect that node from the network. If the system uses proof of work consensus, the network should have enough computational power based on the network's available nodes. Also regularly monitor the computing power to ensure no one is misusing it. For instance, like if nodes are getting more computing power, for instance like 51% computing power, then they can run double spending and other attacks as well. So you have to continuously monitor the computational power. It is not very low, it is not very high. In addition, before joining the blockchain network, perform node authentication. You can use this mechanism as well to perform node authentication. For instance, like by using requesting network joining fee, validating node connections and monitoring node activities. However, some of these activities are maybe more related to the permissioned blockchains, but if you are building the application on permissionless blockchains, then you can incorporate the feasible countermeasures from this list. The double spending is categorized under data consistency attack. To spend the same transaction twice, where for instance like the attacker can spend the transaction first time and then using the same transaction he can spend second time as well. For instance, like in blockchain based healthcare application, the attacker can change the transaction state and spend the same transaction twice. So here we have business asset, our digital asset, and the integrity is the security criteria constraint of business asset, and the system asset is ledger. So the attack scenario belongs to the 51% and more computing power, as I previously stated as well. So the attacker uses 51% or more computing power to control the network, to weaken the peer-to-peer network to perform double spending, for example like insurance frauds. This vulnerability can also affect the availability of network resources. The attacker can trigger selfish mining, prevent new transactions from gaining confirmations, and blockchain forks. However, this vulnerability is practically impossible on high computing power blockchains, for example like Bitcoin. Bitcoin has a highest difficulty level currently. So this attack may be impossible on Bitcoin, but this attack is possible on small blockchain networks, those who have a less computing power as compared to the number of nodes they are connected. For instance, there are different cryptocurrencies who are using proof of work consensus and they have not much computing power, then they were targeted with double spending attack. To mitigate double spending attack, once building the application, the developer should implement a power monitoring tool to monitor the computing power of nodes continuously and restrict the nodes who are reaching a certain amount of computing power. For instance, like the one node or the number of nodes, if they are doing pool mining, they require 51% and more computing power to disrupt the blockchain network operations or blockchain services. So the power monitoring tool can monitor this computing power of nodes continuously, and if they are reaching, for instance, like the system can detect like okay, they can reach to 51% computing power or more, they can restrict the amount of computing power from those nodes, and then they can bring down to the level where the risk of 51% is mitigated, or it is reached to that level where it say like, okay, the system is no okay to be performed, so there will be the less chances of double spending. Also, there are other countermeasures, for example, like incorporating transaction fee as an incentive mechanism to keep nodes honest in blockchain system. For example, like previously we discussed crypto economics mechanism, incentive layer, where the Bitcoin is providing the mining rewards to the honest nodes who are performing legally, and they are contributing with their computing resources to the blockchain network. So they are not hurting, they are contributing in the blockchain network. So performing like consensus mechanism, verifying and validating the transactions. So to introduce the incentive mechanisms to keep the nodes honest. Use a pluggable consensus mechanism to facilitate consensus diversity based on the blockchain system's requirements. For instance, if you have not much nodes in the network, then maybe you can use practical Byzantine fault tolerance. If the system requirements is based on like you don't have much computation power or mining, you don't want to include the mining, then maybe you can use proof of stake. So so select the consensus mechanism which is more suitable for your business needs, for the application which you are building. Furthermore, the study states that increasing the number of confirmed blocks would decrease the double spending threat. For instance, like block confirmations. This topic, block confirmation, we also discussed in our previous lectures as well. So the block confirmation, the more secure against the double spending threat. Also use a closed form formula to calculate the likelihood of double spending in a race attack. So there is another kind of attack, race attack, in which the nodes can compete with each other to solve the next block quicker than the other legitimate or the honest nodes on the blockchain. So the attackers can use this race attack to increase the likelihood of double spending. So in addition, to mitigate double spending, enhance network policy to guide how to set a block confirmation number considering the value of the transaction. So these are the some security controls which can be implemented in blockchain based applications to protect against double spending and cyber attack. But as we see, like there are other type of security threats of blockchain based applications, and there are other type of security controls as well to mitigate those security threats. So it is up to the professionals who are building the blockchain applications. They have to clearly distinguish, clearly identify the assets which they are using in their blockchain applications and what type of assets to protect against different security threats. So in summary, in this lecture we discussed security risk management, where we explored the security risk management domain model that provides the security risk management principles in three different concepts, in three different conceptual levels. Assets related concepts, where we identified what assets to protect from different security threats. Security risk related concepts, where we explored different security threats and vulnerabilities and the impact of those security threats and vulnerabilities on business assets, and the security risk treatment related concepts to implement security controls, countermeasures to mitigate the security risks. We performed the security risk analysis of back pain patient healthcare application case, which is implemented or which was implemented on traditional technology infrastructure, and we identified different security threats, and then we present blockchain as a countermeasure solution. So we discussed like blockchain provide different security controls by design, which can be helpful to mitigate the security threats of traditional technology infrastructure based security threats. We also explored blockchain is not a silver bullet. So various security threats can appear or can happen on blockchain based applications as well. So taking the same healthcare application case, we build a blockchain based healthcare application. And then we analyze the security of blockchain based healthcare application. where we explore different security threats can happen on that application. And in that, we discussed cyber attack and double spending in more detail. We also discussed how we can mitigate cyber attack in in blockchain-based applications and how we can mitigate the double spending. We explored different possibilities, different countermeasures, and different techniques that can be viable solution to mitigate the security threats of blockchain applications.